We started measures of spread last lesson. We ended up with a formula which worked from a list of numbers. If we call the list of numbers x, what did we do to those numbers in the formula that we had at the very end of last lesson? Yeah, we subtracted the mean from each of them. That was the first thing we did. And there's something else before what you said next. We squared them, because otherwise you get pluses and minuses that cancel each other out when you add them up. Yep, then you divide by how many there are to scale that total back down. And then we square root that, and we call that the standard deviation. Yeah. Some of you said you already come across that in, was it psychology and biology? And I said there's some notation, another symbol that we use for that. Anybody remember what that symbol was? No, that's that one there.
Oh, that's sum.
Yeah, that's the sum. There's another symbol we use to represent the standard deviation. Go on, you've got it over there. Even if you just describe it.
Is it like the little circle there?
Yeah, it's a little circle with a little sort of tail going up there. Okay, that one there. Circle with the tail going up there. And we said what that was called as well. What's this one over here called? This one over here is also sigma. That's uppercase sigma. That's lowercase sigma in the Greek alphabet. So that's lowercase sigma. And we did one example last lesson of working out the standard deviation from a set of numbers. So that above that line is the actual key thing, and that you need to learn. So what we're going to do that now is we're just going to do it on another couple of sets of numbers just to check you can use that correctly. So if I call this example 2, because I think we've had one already, and we'll find the standard deviation of, and the numbers are going to be 10, 11, 12, 13, 14. 10, 11, 12, 13, 14. Okay? So if you're going to do it in using this formula, the thing I'd suggest you did like last time was have a little table, have your x numbers going along in your table. Now just from looking at that, you should be able to tell me what the mean is, what x bar is. Yeah, purely by the symmetry, that's right. X bar here is going to be 12. And the next row is going to be x minus x bar. So you're going to take 12 away from all of those values. I'm going to start at the right hand side because it's positive there, which is easier. And the whole point was that if we added those up, that would always give us 0. That's where we did the squaring thing up here. So all of those numbers get squared. So Emily, what's above the line is just a recap from last lesson. Okay. So we square those, then it's a case of adding those up. Can somebody beat the usual person to adding those up?
10.
10. Okay. We divide that by how many numbers there are, which is 5. And then we take the square root of that. So we get root 2. Does anybody know what root 2 is to, say, 2 or 3 decimal places?
4.
1.4?
No, I was just guessing. Don't put that
1.414. Okay, it is 1.4 something. Yeah, okay. So, there we go. So the standard deviation of that set of numbers is 1.414. Okay?
Is that the answer?
That's the answer for the standard deviation, yeah. Then, if we look at another set of numbers, we'll do the same thing. So, again, we'll find the standard deviation. We'll have the same amount of numbers. We'll have 5 numbers again. 5, 6, 12, 18 and 19. Can you have a go yourself then at just doing it from that list of numbers, please? Okay. So I'm going to freeze it on the board in class, but I'm going to keep writing for those who are watching. So you should have found already that the mean of both sets of numbers is identical. You would have realised as well that the second set of numbers, the last example, example 3, the numbers are more spread out. So you should be expecting what? Comparing your standard deviation answer for the first one we've done today and the second one, what would you reckon about the standard deviation for the second lot of numbers today? It should be bigger, yeah, they're more spread out, so you should be getting a bigger answer. Does anybody have an answer? Does anybody have an answer for adding up the squares?
120.
170 is right for that bit. Okay.
I have an answer.
What is it, Callum?
It is 5.83.
Which is exactly what it says on the board, and that's correct. Good.
Is it?
Okay. Yeah, it wasn't up there the whole time. So yeah. Okay. So 2 sets of numbers. The means were the same for both of them. Where the spread is bigger, the standard deviation is bigger. Write that down? Yeah. Okay.
So what is the standard deviation?
It's a measure of how spread out the data set is. So if the data set is more spread out, it will have a larger standard deviation. Okay. So if you want to put something down about that, so the last 2 data sets had identical means. But question 3's data was more spread out. Or sometimes you'll see that it's described as being more variable, or has more variation. And that's why that had a larger standard deviation. There's another thing you may come across. There's another measure of spread other than the standard deviation, and it's called the variance. The variance is this. What is that?
That's just the table, but not square rooted.
Yeah, it's just standard deviation, but not square rooted. So the variance is equal to the standard deviation squared. What's the standard deviation if you just forget to do the square rooting bit? So that's what the variance is. And that will become a bit more significant as we go through the course. Now, if you've got a lot of numbers, working out all these differences, particularly if they're not nice numbers, if they're horrible decimal numbers, is quite fiddly. So there's an alternative formula that you can use for the standard deviation, which you need to learn as well. So an alternative, and I'm going to put here easier, because it does make calculation easier, an alternative easier formula to work out the standard deviation. Which is, you square all the x numbers, all the numbers you have. You add up those to get the total of those squares. You divide by how many numbers there are. Then you take away the mean squared, and then you square root it. Now you haven't got to know where that comes from. You haven't got to prove how that formula and the other one are the same as each other. But if you look in your textbooks, if you're interested, if you're not interested, it doesn't matter. But if you are interested, if you look in your textbooks, certainly in mine it's on starts on page 56, so if yours has got the same cover as mine, it's the same edition, on page 56, it's section 3.7, and in there it takes you through some algebra, which basically shows that the one we had before can also be rewritten like this, and they are the same thing. As far as we're concerned, I'm not going to go through and prove it. You don't need to know that. You just need to be able to use that formula you've got there. Okay? So, we're going to have another set of data. We're going to introduce something else to it as well. And we're going to have to adapt our formula a little bit too. So, this is example number 4, I think, isn't it? I'm going to draw a table out which is going to have a heading over on the left, accidents per day, that's one row. Below that I'm going to have frequency. You will need another 4 rows below that eventually, another 4 rows. No, I'm going to change my mind, 2 rows. Then I might change it back again to 4 in a minute, I'm not sure yet. Give yourself space for 4 rows after that. And there are going to be 7 columns after that. 0, 1, 2, 3, 4, 5 and 6. Beautifully drawn out table, if I may say so myself. Right. Emily, you think you're the last person to arrive. Can you nominate somebody, please? Callum.
Yes.
Would you like to work out the standard deviation here using the first formula we saw or the second formula we saw?
I'll get first.
First.
Yes.
Okay.
So I get to nominate some.
Maybe later on, we'll see.
Okay.
So, let's just put down somewhere on your bit of paper then. The first formula we saw for the standard deviation was that. Now, what's the issue we've got with the table in that formula at the moment? Patrick?
We don't have a mean.
We don't have a mean. We can work the mean out. How would we work out the mean from that table? Yep.
Would you times the number, the frequency by the number of accidents?
Yep. If we call those x numbers, if I do that, yep.
And then you just add them all up.
Yep.
And that will be x. And then divide that by the frequency.
Total frequency. That'll give me the mean. Okay. So yeah, I will need to know the mean for here. But what is missing in this formula that's in the table we've got at the moment? Patrick?
Is it like a set value that you have to because they give you different, they give you the frequency, but in the past we've had something to
Yeah, we've got frequencies here, okay? You don't really want to write 0 out 5 times, and you don't really want to write 1 out 8 times. So what we're going to do, we're going to adapt the formula here to deal with the frequencies. It will still have an x minus x bar squared in it. But we will have to times that by the frequencies before we add them up. And instead of dividing by just calling it n, what is n going to be based on the sort of frequency table? Cumulative frequency. So how could I write that down in symbols? Sigma f. Yeah. And I'll square root it. So that is like the old formula for the standard deviation adapted for use with frequencies. Okay? So that's the original formula for standard deviation, but it's been adapted for use with frequencies. So you spell frequencies, or should it be YS on the end? Range gone. So, we need to do this calculation up here first of all to find the mean. Can we have a go at doing that? Timesing the x and the s together. That's going to be 5, that's going to be 8, that's going to be 12, and so on, and add those up. Is anybody going to be brave and just have a go at doing some old-fashioned timesing and adding up? You could all do it, see if you get the same answer. You could work in pairs. You got calculations? Go on, have a go at working out the mean, first of all, by doing this bit here on that data. Tell me what you get. What is sigma f of x? What is sigma f? Yes? What do you reckon the mean is?
8.
Not correct. The mean can't be 8, because no values are bigger than 6. The mean's got to be between the smallest and biggest value.
I've got 2.04-ish. It's a bit of a decimal.
Well, a bit of a decimal. There's nothing wrong with it being a bit of a decimal. It's not the answer I've got here. I've heard something correct from you, James.
It's 48.
That is 40.
I got 1.8.
That's correct, yeah. If you do nothing plus 8 plus 12 plus 9 plus 8 plus 5 plus 6, you should get 48. That's all the f numbers times by the x ones added up. That's 0 times 5, 1 times 8, 2 times 6, 3 times 3, and so on, added up. Sigma f, you must have had over there correct.
Oh, it's 26.
26, yes. And that gives a mean of 1.846. Should we just call that 1.85 a minute? 3 significant figures. 1.85. So if we're using the old formula, the next row is going to be x minus x bar, and I reckon we can get away with squaring that at the same time. So here you will need to do 0, take away 1.85 and square it. You need one, okay? It's a maths lesson. If you got a phone, you do it on your phone.
How many decimal points do you have?
If we did three significant figures, so what's the first value in here?
3.4.
Okay, 3.42. Now, just stop a minute before we get all the way across, because you're just going to get so bored by doing this all the way across, and it's just going to be such a repetitive task. We'll just leave this blank for a minute. What would the next row be then? If we're using this newly adapted formula, what would we do on the next row? We've got x minus x bar all squareds. Sigma fx, sigma thing won't be a row. Sigma is adding up numbers. So I've got that bit there so far. I would next have to do that. I'd have to times that by the frequencies. So my next row here would be f times by that. So I've got to do my frequency 5 lots of that 3.42. What would that be? 17.1. And we'd have to do all the way across. But we're not going to, because doing that would just be boring. So we're not going to.
Can I put that on my sheet?
Yes, you can put those on your sheet. I put it on my sheet, you can put it on your sheet. And it would be boring and it would be tedious.
Do we have to do it in testing?
No, that's when we're going to use this other formula I showed you a minute ago to speed things up. So,
I'm sure I have the wrong formula.
no, I wanted to show you what would happen if you did that one. It's an awful lot of work and it takes forever. So it's not a wrong choice. It's just I wanted you to see that. So, a minute ago, or a few minutes ago, I gave you this other formula here. And I said that formula there also works. Now I'm going to write that one down again, just so I can move that bit of paper up in a minute. So I said that was our alternative formula. Now, how do you think I can adapt that formula? The same way I adapted this formula to this one, how do you think I can adapt this one here for use with frequencies? How do you think it will appear? Swap the n for a sigma f. Yes. What do you think? Where do you think an f might appear somewhere else? Here. Yeah. Okay. Sigma fx squared. Okay. We'll keep the x bar squared there. We'll keep the square root there. So this is the second formula adapted for use with frequencies. And it's much easier to calculate from a frequency table using this formula than it was that other one a minute ago where we had to do loads and loads of sums and horrible decimals were cropping up all over the place. We'd already got 3.42 and squaring that and getting stuff. So we're going to use that version there instead. So, back to our table. This is why I said we have about 4 rows or something. We're going to ignore, for a minute, these last 2 rows, the rows that we labelled boring. Okay? We've got an x row, we've got a f row. We're going to ignore the next 2 rows. Let's just see if I can cover those up for a minute. Convenient pen. Okay, cover those 2 rows up. So what would be a good row then, do you think, to have here if you're going to use this formula?
Sigma fx squared.
Sigma, if anything, won't be a row.
Sorry, fx squared.
Fx squared. Okay? Now you can either have an x squared row followed by an fx squared row, or we can do it together. Fx squared means f times by x squared. So here, that's 5 times by 0 squared. 5 times by 0 squared is 0. Okay? And that's far easier than going into those horrible decimals we did a minute ago. So the next one, Callum, can you nominate someone, please?
I choose Lucy.
Lucy, what will it be here? Fx squared. What's the sum? What's the answer? Yes. Okay, Lucy, nominate someone, please. No, you can't. No, can't nominate people who've already been nominated at the moment. Next one, then. 6 times by 2 squared is 24. Can you nominate? Beth? 3 times by 3 squared, 27. Nominate? 2 times by 4 squared, 2 16s are 32. Nominate?
25 is 125 squared is.
Yeah. And Patrick, nominate?
I don't actually know anyone's name.
Oh! Patrick, behind you there are 4 beautiful girls who would like to introduce themselves to you. Can we go along and give Patrick your names, please?
Hi Patrick, I'm
Right, Patrick, take a choice. Which one do you want? This is only for answering the question, Patrick. Only for answering the question. Gracie, last one. Right, what are we going to have?
36.
Yeah, okay. 1 times 6 squared is 36. Okay? Right, okay, so there we go. We've got those. Now, we've got fx squareds. Now's the time for sigma to come into play. We need to add those together. Okay? Can we add those together, please? Gracie, can you nominate someone to do the adding up?
Wait, do we not need another column? Is that it?
Do we need another column? What column would you like?
I don't know, but
I
I
think
left
you
an
need a
extra
row, don't you?
another row even, because I left another row.
No.
You said
I did say up to 4, didn't I? Yeah. You may have a vacant row in a minute. Right. Have you added these up, Liv?
I think it's 152.
That's what I've got here. 152. Because we're using this formula here, okay, the one I'm pointing to here. So the sigma fx squared is adding up the fx squared, so that's right. We need to divide that by sigma f, which is adding up the f numbers. Has anyone done that? And Liv, can you nominate someone to do that?
I nominate Becky.
Thanks for that.
I'm getting
26 I agree with. Okay, so that's that bit. No, I meant to leave more room in here. What have I got to squeeze in here? I ought to have left more room. Yeah, take away x bar squared. So take away x bar. Have we worked out x bar for this data set? No, we haven't, have we? X bar. Okay, so I don't scrub that out there. I'll do that on the line below. I think it makes a bit more sense. So we've got that. We need x bar. Right. How are we going to work out x bar from that data set, James?
Oh wait, from which one?
From this one here. How are we going to work out x bar?
Oh, you just take all the frequencies and it's the mean.
Yeah?
So you just times all the frequencies by the action. So it's,
We did it.
it's sigma fx minus over sigma fx.
Have we done it for this data set already? Oh, we did, yeah, 1.85. You're quite right. We did, didn't we? Yep. Okay, so 1.85. So putting it all together, I'm just going to shoot that up here a minute. Put these together. We had a minute ago then, sigma fx squared. This is what we're doing. Sigma fx squared. That's what we're trying to do. We had a minute ago, that was 152 over 26. We know that's 1.85. We'll square it and we'll square root it and we will get our answer. What answer will we get? Well, I've got 1.56 down to 3 significant figures, and that is correct. So we are agreeing there.